We are live and we are here. So I'm going to give everybody just a couple of minutes to get logged in, but I have a very exciting announcement to make. Officially, I am launching the service training program live at chilleracademy.com. And I do specifically reference it as a training program, not so much of a course. So it's far less of a you go through this structured content to learn these things like a traditional school environment. No, this is a series of guides to help you perform your daily work so that you can actually understand how to approach effectively and efficiently different repairs or different circumstances, whether it be from recovery all the way through to charging, pressure test, evacuation, trying to figure out your GPMs. If you're trying to troubleshoot approach to a heat exchanger, maybe you've got your EXV you're having trouble with, or anything that you need. That's one of the cool things that I want to do with this course or this program is when you get into it, if there's a specific thing you're looking for, like a specific training or procedure. If there's a specific procedure that you need because you're about to go do a job for that, then just let me know, right? Reach out and I can work out getting that procedure built and then uploaded for you, ideally within time, especially if you give me a little bit of a heads up ahead of time. But either way, even if that's not true, like you're going to still get direct support via the community, via comment section. You're still going to have all of those things at your disposal to just do better and increase your likelihood of success and not have to worry about failing at it. I know that was something that really grasped me for a long time in the early days was just a lot of this stuff is fairly intuitive and you think you're on the right track, but it's hard to just get rid of that pit in your stomach of am I? Like, is this the right way to go? Am I doing the right thing? It's really like that was something I really struggled with for a long time. And I know how that feels. I remember how that feels as early in my chiller career, just your HVAC career in general, but especially your chiller career. So I, yeah, I built this to help with that specifically. And I'd love to help you out over there. It's taken a lot of work to get it where it's at, and it's been really fun because I've gotten to build an actual team on the back end of advisors who help me with that and have helped kind of talk through and navigate the different procedures that we're working on that's in there. Either way, just as we get rolling here, I just want to throw that out there right here in the front that officially the service training program is publicly available if that can help you. It is more expensive than some of the other trainings I've done. It There's a lot in there, and it's taken a lot of resources to put this together. So hopefully your company or somebody can help sponsor that on some degree. I know a lot of people have had a lot of success with that. Otherwise, just reach out to me. Let's talk about it. But with that, we do have a really good question to get us kicked off here. And today, our primary topic is centrifugal service questions. Now, if we need to dive into some others, that's okay. But for the most part, if you have anything that's specific to centrifugals, let's try to keep on topic there, and then we'll go from there. Otherwise, so the first question: what is the function of the micro board and I/O board on a York YK chiller? It's actually a really good question because we're very used to having like a lot of the control circuitry we have is all kind of encompassing. We're having control boards come out that like everything kind of runs through the same boards. You don't have like um, dedicated modules to do specific jobs. Now, I/O, just to clarify there, is input output. But that doesn't mean that there's not inputs and outputs on the micro board, which is the main board. So if we come over here, you'll see the micro board is here. And you'll see that we have the SD card slot up here. So this is a 3630 module. The 2430s and 1730s look slightly different. They're not that different. But anyway, this is your micro board. This is your I/O board. So these have a ribbon cable right here. And these cables are actually a common point to have issues. So if you start having like a start-stop call issue, or your pump heater, or your oil, or yeah, the pump heater, something like that's not coming online. Pump heater, what am I saying? The oil heater is not coming online, something like that. Check this ribbon cable, because it could very well be a problem. One of the common things that I've done in the past is you can simply just do an unplug and replug on both ends of that cable. And if it was having a connection issue, that can help with that in some scenarios. Either way, so this is your main brain. This right here, this processor is actually the processor that runs the entire chiller. So what we're doing, these are still inputs and outputs for this module up here. Now these are your power rails. This is communication going through your ACC and VSD and such. But up here, these are your sensors. So you've got your temperature sensors, your transducers, your flow sensors. All of that is going through up here. But those are very light loads. They're pilot duty devices. Okay. So they're not putting any major stress on the circuitry for the main micro board. And that is where this I/O board comes into play. So not everything in this I/O board is say a heavy load. For example, your input outputs. So right here, these are your input outputs. I'm sorry, your start stops. These are your start stops for the chiller from the automation system. So it's coming in, tying in here. That's not a major load, but that's also where it's just kind of the I portion, input output board. Okay, so this is where your inputs coming in from other components, automation system, all of that can come into here. And then over here we've got actual like mechanical relay contacts that are handling our outputs and our heavy load pass-throughs. For an example, these relays here are what handle your oil heater. So your oil heater passes through these relays to get engaged and get powered to maintain your oil temperature in the sump. So that is the primary function that separates why the I/O board exists compared to the micro board, and why they're two separate boards. They have basically those two different functions. This is where your actual load duty devices are coming in. Like if you're running a pump, a starter, your pumps would tie in here if the chiller had direct control of that. And then up here, we're just running very light duty devices, okay? Flow sensors, transducers, temperature sensors, things of that nature. That's all that the micro board itself is doing, other than communication, is powering the display panel. All of that is handled through the micro board, which are very light loads. Is also the most expensive board in the whole machine. So there's that. Yeah. Anyway, good question. Really good question. Let's see. What is our yes. Yes. Well, you got to think, mistakes on RTUs, it comes back to the scale of what you're working on, right? So with an RTU, we've got typically cheaper components, a smaller refrigerant circuit, so turnaround time and the scale of the components themselves. And when I say they're cheaper components, it's usually a scale issue, right? The scale, the size that it needs to be is smaller, which inherently is going to be a cheaper cost. So that's where doing RTU, or say just non-chiller work, can be cheaper at times. Is it doesn't take as long to recover. The evacuations don't take as long. The requirements we need to hit aren't as strenuous. Things of that nature really come into that cost difference as to just why there does seem to be so much of a different cost for what in some cases they're not that much different of a repair, really. Um, yeah, kind of my thoughts on that. Scenario: YK faulted on a PRV actuator fault. Find actuator bad position showing recalibrate. All right, let's grab this one over here. If y'all want to know about the fire we had, I'm happy to talk about it for a few minutes at some point in this stream. If you're not interested, that's fine. I just thought I would ask before going on a spill about it. It was pretty intense, I'll say that. But yeah, just throwing it out there. Okay. Scenario: YK faulted on PRV actuator fault. Find actuator bad. Position showing relatively 60% open and needed to be replaced. What's the procedure to install new one and recalibrate for proper operation? Okay, so installing a new actuator and then calibrating. So what is really important for the installation procedure, one, the wiring in there can get a little tricky, and that's because of it's because of what that relay, or that, not the relay, the actuator can do. So it's more than just a open and close floating point actuator. That would be the style that actuator is. It's a floating point design. Ooh, I actually have a picture of this. But the termination points, so we also have relays in there. So let's go find a picture and let me show you. Give me 1 second here. Come on, I know I've got a picture in here of that. Actually, got a couple of pictures we could look at. I want to show you the wiring first, though, before we get to the linkage. This is what happens when your library is a little bit too much of a mess. Here we go. Okay, so this is what that actuator wiring looks like. So yeah, this can get a little complicated. So I'd say this is one thing to really pay attention to. Make sure everything is wired and labeled appropriately, and you're really identifying what goes where. Also, another thing to verify is that depending on how old the machine was that you're replacing the actuator on, make sure that the actual wiring to the new one is exactly the same as the old one, and that things didn't slightly get moved or pivoted around. Because if memory serves, actually this one in this picture was an older one, and the new actuator that replaced it wasn't a major difference, but it was just ever so slightly. I don't remember what was different, but I think something was slightly different on the new one. And it took us a minute to sit there and look at the thing and be like, okay, what are we missing here? Either way, so paying attention to this wiring is going to be one of the major things that's going to mess you up. So more than just having your open and close power wires, you've also got the relay up here that is going to identify when the actuator moves into a full closed position, because there's an internal switch in here that gets triggered once it hits its full rotation to one way or the other. And we have to make sure that when we swing into the fully closed position, that relay sends a signal back to the control board so it can verify full closed position. Now, that brings us into our next thing to pay attention to. Come back to that other picture I was referencing. Let's grab. That's not the right one. grab this one. So, well, you can't. We'll work with it. So down here, this is your PRV actuator. This is your VGD actuator. So we'll use this one as our example for now. What is important, probably the most important thing with installing one of these is that we get the vanes. Now I'm just going to use the VGD here as the example. We're going to use we need to make sure the vanes are fully closed at a bare minimum, meaning that actuator has been driven to the full closed position, which this should be a 90-degree actuator. So we're in a fully closed position, and our end switch for closed has been triggered. We're sending that output out, and then we're going to pivot our armature to where we can move to a fully closed position on the armature. So for this actuator down here, that should be a full swing to the to clockwise, if memory serves. So we want to make sure that where the arm for, or the shaft for the guide vanes is positioned is in a fully closed point. That way it matches fully closed at the vanes and fully closed at the actuator. And you want to make sure you also put a little bit of pressure on it. Not like hard, like you're forcing it, because then you'll end up putting too much stress on the vanes themselves. But you want to make sure that it's solidly closed, because if you don't get this part right, part of what will happen is the vanes may allow too much leakage through them at startup, which is going to cause your motor to go into an overcurrent because the vanes aren't fully closed properly. So if this mechanical linkage is not put in just right, then you could be causing an overcurrent issue at startup. That'll probably be the primary symptom that you're going to deal with. In addition to, it's going to have a hard time unloading as much as it needs to when it needs to close the vanes, stuff like that. So just be aware of that in the process. Okay, so we've made sure that our actuator is at a fully closed position. Our closed relay output is triggered, and that we've manually pressed the shaft for the PRV in this case to a fully closed state. That by that time, that's when we can install our linkages. Now, the paint from the factory should be fairly accurate, because some of these linkages will have like little extension bars. This particular one doesn't. It's just a pretty straight bar, but some of these will actually, they're like a two-piece, and so you can extend or shorten the actual bar here. So using those factory paint marks can be a really good benefit. If you are going to have to adjust anything like that, marking some things with a Sharpie before you remove it is also really helpful. Now, in the event that you're coming in behind somebody else who did it, maybe they didn't do it correctly, but you're still having issues. Well, in that scenario, you kind of come back to this linkage bar may be part of your problem. So if they did not verify the actuator was in the correct position, and if they did not verify that the arms were, or the shaft was fully pressed, and like I said, put a little pressure on it to make sure that it is fully closed. It's not just ever so slightly cracked open. You don't want that. Then you can install the actual arm and set it in place. And these are just a 90-degree rotation. So that's all you're going to get out of this. And that's all you should expect. So as it rotates around, it will pivot up. So like this one, as it spins clockwise, it's going to pick that armature up and slide, in this particular case, a VGD ring out. But the calibration process is pretty similar from the VGD to the PRV. It just slightly different context. But either way, yes, with everything closed, set your linkage between the actuator shaft and the PRV shaft, then set your linkage to that point, and then you have to just stroke it. So then when we get into calibration, I just come back over here. when we get into calibration, with the machine off and the unit switch set to off, you have to make sure that's in the off position, and I'm pretty confident you have to be in the service mode to do this. With everything positioned and you've got the sensor mounted, so you may not have had to remove that throughout this time, but with the sensor mounted, the position sensor, which is this little box right here, that is a rheostat in there that's sending a resistance back to the microboard. As the microboard reads that resistance, it knows that, okay, X ohms is X position, Y ohms is Y position, there's my 0 and my 100, and then I'm on a linear scale in between there in order to have my physical position of the PRV shaft. So the easiest way, and I've done this the hard way before, the easiest way is once you get all this positioned, you just initiate a PRV calibration. And the PRV calibration process is going to stroke it all the way to full close. It wants to see the closed relay trigger, and then it's going to rotate back to full open, and it'll rotate the actuator to the 100% position, the 90 degrees. So it's not actually paying attention to what the position sensor is saying at that time. It knows that this actuator takes X amount of time to rotate. I'm going to rotate for that plus a little bit, make sure that we're all the way there. And then it's going to take whatever that ohm reading is and set that on the scale as 100%. Then once you do that, then it basically recalibrated what the ohm values are for 0 and 100% based off of how the actuator is expected to function. If all of that goes correctly, then you should get a calibration passed, and everything will go back to normal functioning from there, and you should be good to go. So that would be the procedure to removing the actuator and then reinstalling it, calibrating it, and then testing it. Make sure that as you're swinging, it's very important that that linkage in between there doesn't get into any kind of binds. It's not going to have any issues getting hung up in a spot. And you just have to watch it. It should be a nice, gradual, easy and smooth flow from 0% to 100% as it's going in between there. Okay, if you see it kind of hiccup or glitch at any point, because you can manually open 100%, close 100% from the panel with the machine. I would do all this with it off. Don't do this with it running, but you can do a manual operation on that PRV. So just watch it. Make sure that it's not binding up at any point, because that will only just cause further failures down the road. Good question. Is the process the same as if replacing the VGD actuator? Yes. Yeah. So I know I talked about that a second ago, but yes, they are essentially the same. The difference between calibrating the VGD and PRV is what the device is. Not to get too like obvious with it, but it is important that the VGD be able to go to full open and get calibrated to that point so that it has maximum flow. And I guess maybe, let's see, let me make sure I'm saying this right. When I've done mine, I've calibrated mine to full open instead of full closed. So I will make sure that I can get 100% diffuser gap whenever I'm needing it, and then I will just close off as much as that 90 degrees will give me. So I guess that would be one difference that is important here. I'm sitting here thinking through it. I'm really glad you brought that up. I've calibrated mine in full open. I'd have to go back to the manual to actually verify how the manual says to calibrate, but that's how I've just done mine intuitively. I've calibrated to full open, moved the armature shaft to a full open position, moved the actuator to a full open position, set it there, and then allowed it to just verified operation allowed it to go through its thing. It doesn't have the same calibration procedure but we're not monitoring position. So that's the whole point of calibration for the PRV, is we are actually monitoring the physical position of the vanes, but we don't do that with the VGD. So we don't have a potentiometer giving feedback or reference to that. Now I say that, I think I'd have to verify this. I think some of the newer machines might actually starting to do that, because I was reading the one of the newer YK manuals the other day, and I think it actually made reference to the VGD position. So maybe that's something on a newer model that they've started doing, but for sure the older models that wasn't the case. So anyway, long story short, they are slightly different. I calibrate to open. Other than that, most of the process is relatively the same. Okay, let's grab this one. All right. Please explain Trane TU software in simple words. So TU is Trane's service software that works with their UC control system, their new Symbio UC controllers, which for us a lot of times we're dealing with the, at least on the centrifugal side, it's the UC 800, and I think it was the UC, was it the 400 or 600 I saw on some of their air cooled models. Either way, it's going to be a UC controller. So these will have a cable that's using a USB B, so the kind of the boxy one that we would know, like the old school printers used, if you're familiar with that whatsoever. But so you've got USB A, B, and C, right? We all know what the USB C is. That's what all of our phones use today. USB A is the traditional USB that like a thumbstick would traditionally work off of, but USB B is the one in the middle. So it's the one that looks like a box. And several other tools use these as well, but that's what the Trane TU is going to function with. So you may plug a USB A into your laptop port, and then it'll be a USB B that plugs into the controller directly. With actually this chiller here behind me, they actually routed a cable from the UC 800 to the side of the panel, so you don't even have to open the panel to plug in and connect to it via the software. You can just do it through the side of the panel, and they've got a little plug. And Trane's tried to make that part a little bit easier, but so in simple words, it is a service and commissioning software that requires a license to use and operate, which is different from the previous TechView software. That was an open software that was free to use as long as you're in the right country. That is one aspect. Either way, it was free to use, and that's no longer true with TU. TU, you have to have a license from Trane, and you have to input that license to use the software as a service tool. And that license does cost money. You also have to find a Trane dealer who's willing to sell you a license key. That's so if you don't have a connection to somebody who is willing to do that, because it's been my experience that most Trane shops, if you're not a part of their network in some way, they won't sell you a license directly. That's just been my experience. Now, you can use this software for troubleshooting, and it's going to give you a lot of the same information and more. It will give you more than what you can see on the front display. The two main things that I think this software is, or the three main things this software is the most useful for is binding. So you have to bind sensors to the chiller. If you replace one, or if you replace a board or a module, something like that, it has to be bound, which is basically assigning an address. That module has its own IP address on a communication network, similar to a bunch of computers. So whether that be the modules themselves or even the sensors, the transducers, as an example, those have their own little IP address that works off of the network. That is the control wiring that runs throughout the chiller. So we have to tell the main controller that that device is a transducer, and a low pressure transducer at that. Otherwise, it doesn't know what to use that information for. So the computer is really good at, or the TU software is good at helping with that binding process. Trane has an interface that you on the display you can get into to do a on the newer software versions. The older ones didn't, so you need a newer version of the TU or UC controller software. But you can get into the binding view there. Now, I personally haven't had issue, but I've gotten a lot of reports that sometimes the display binding can have some weird glitches, and the only way it was able to be resolved was then using TU software to do it that way. So just as one of the main benefits, binding is definitely one of them. Another one is data logging and being able to pull a full data log onto your computer through that software. It is really good for that. If you want to walk up, take a full snapshot for a PM maintenance or even a service, whatever's going on, TU software is really good for that. The final thing I would say is commissioning. It is very, very good at commissioning. Kind of necessary, to be honest. So if you're going to fully commission a machine, or if you have to replace the controller and basically commission it from scratch in the same way that the factory would normally have to, then you'll need that TU software to accomplish that. You're not going to be able to do it otherwise. In terms of actual troubleshooting, it is my experience that the display itself is actually, it gives you enough of the information you need. It may not be laid out quite as smoothly, but if I'm strictly troubleshooting, I typically won't connect the TU software for just that. I will just use the display screens and work from there. Now, if I need to dive in deeper and get more in depth, or take some control, do some manual operations, anything of that nature, then I will break out the TU and use it further from there. But it won't be just something I go to immediately plug in as soon as I walk up to the chiller. So that is how I would describe the Trane TU software in the simplest words I can. Okay. Can you touch on how the thrust bearing proximity sensor probe works too? Interpreted. Yes. Bear with me. Hope y'all are having a really good start to your week, by the way. It's been crazy on this end, for sure. Okay. Can you touch on how the thrust bearing proximity sensor probe works too? And what are the values telling us? How should they be interpreted or used during troubleshooting? So, the proximity probe is sending out pulses, and it's monitoring the thrust bearing collar that's attached to the high speed shaft of the compressor. So Let me see if I can get a good picture here where we can look at one. Give me just a second. If I can't find one relatively quickly, we'll just move on and I'll explain it. That's a YT. Let me find a YK. Do we have a YK in here? Oh, you know what? We could use this. Here we go. Yeah, let's use this. Okay. So we'll use this picture as our as our example. So I don't have a fast one to grab. So we have our high-speed shaft here for the YK. So this is directly attached to your impeller. You have a bull and pinion gear. So it's your pinion, this is your bull, helical gears, step and speed up, motor shaft here. These also have thrust collars on them as well, or technically the thrust collar is over here. And then our high-speed thrust collar is here. And then the high-speed thrust bearings, I'm sorry, right here is the collar, right here is the bearings. Now this is a very small space here. So keep that in mind. Very small space. And basically these collar, the bearing itself is just kind of a set of touchdown pads. It's a set of, I wouldn't say they're, rubber's not a good, they're a set of pad points that when there's extreme axial shift, so a surge, for example, and this impeller gets driven one way or the other, but specifically to the back, these pads are able to do a slight touchdown and prevent a catastrophic failure from just extreme metal slamming into each other at high speeds. Because keep in mind, this shaft here is operating at 20-something thousand RPM most of the time. So our sensor is right here. So our D housing sits right about here and right about down here. Okay, so the big housing that the coupling sits in, that the motor shaft is also inserted into with our coupling here. So this is where you're inside of that D housing, and this is the high speed cover, which is the thrust collar cover. So the proximity probe itself sits right here. Okay, and it's sending out these pulses, and what it's monitoring is the actual thrust collar distance itself. And what it's trying to verify is that thrust collar, when there is a thrust event, an axial load that causes, because when there is an axial load that causes a heavy thrust on the journal or the shaft, we want to make sure that we're not going too far in one direction or another. Occasional touchdowns are going to happen. That's why the thrust bearing is there. But as that thrust bearing begins to wear down, we need to have some form of safety to tell us something has gone wrong here before we have a catastrophic failure, which is the whole point of the proximity sensors, to let us know that, hey, we're in a danger zone and something is wrong with our thrust collar bearings. Now, the proximity sensors themselves can get out of calibration. They can go bad. That is a factor. So it's not a guarantee just because you have some thrust or proximity sensor alarms that is guaranteed a collar issue. And before the proximity sensor, we had this little, say, brass tube that was inserted, that would insert from the control panel side of the compressor into the thrust housing. And basically, instead of monitoring the literal proximity of where the collar is, that collar, once it wore the bearings down to a certain point, would touch down and tap this little brass tube enough times that it would wear a hole in it. Well, that brass tube was full of a inert gas, or actually it may have been full of, no, it shouldn't have been the refrigerant. I think it was just like a very small tiny charge of like nitrogen or something to that effect. But when it released, it opened a pressure switch that the gas in the brass tube kept closed. And that pressure switch, like when that triggered, you were done. That machine was completely shut down. The benefit of the proximity probe was it allowed us a more refined method of control and monitoring, where we could more reliably predict a caller issue, and it can give us some early warnings before we have a complete failure. So if we know that we're starting to have our thrust bearings wear down and we're going to need to be serviced soon, then the proximity probe can let us know ahead of time, hey, I'm about to, or we're starting to have a problem here, and we can take steps to prepare to resolve it and verify, okay, make sure our proximity sensor itself is good, it's calibrated, okay, that's fine, then we've definitely got a thrust bearing problem. It also likely means we're having a lot of major surging issues on this machine, and before, like, that needs to be included in part of our repair and diagnostic is, okay, why are we putting so much wear in our thrust bearings to begin with? Either way, so that proximity probe is giving a feedback based off of that the pulses it is sending out. And then we can take that feedback, and there is a certain threshold. I don't have that threshold off of memory, and I think that's one of the updates I need to do to the troubleshooting guide that I haven't gotten to yet. Let me see. Let me pull the guide up here. Let me see if I have that threshold. I think that's one of the updates I've been needing to work on, and I haven't gotten in there yet. PRV limited lift. Bearing temp. Oil catch. Yeah, it looks like, that's one of the updates that it will be coming out soon. Just so you know, if you do have one of the troubleshooting guides, any updates that are made to those are automatically included. So I'll just re-upload the file to the system, and then you'll have access to the most up-to-date. You're not, like, if you have an older version and you want a newer version, we're still on 2.0 currently, then like, you still have full access to that. And if you're having trouble accessing that, just let me know. I am currently migrating all of those guides to the Academy instead of through the separate store that I had previously, and everything is just going to be housed inside of chilleracademy.com going forward. So if you have purchased those guides before and you see them in your Chiller Academy feed, and I haven't gotten you access to them just yet, just let me know and I can get that updated for you. And then for everybody else, this is a much simpler way to get and have those guides and the PDF downloads. Either way, so I don't have the thresholds right off of memory to what those to what the proximity sensor should be. What I can do though is, so I'm going to take this section of the video and I will upload this as a separate video clip later, as I break down this whole stream. When I do that, I can look those values up and I'll input those somewhere in this section here to where you can see what those thresholds are supposed to be by default, and go from there. So anyway, without knowing the thresholds right offhand, once we start exceeding those thresholds, that's when, again, we have to first verify the proximity sensor is functioning correctly. And if it is functioning correctly, then we get into that's a compressor issue at that point. And that leads into an overhaul condition, because with the old sensor that was just basically the brass tube with a pressure switch, that when that triggered, like, your compressor's done. You're not supposed to turn it back on. I know some people would jump it out and still run it, but that was The last thing recommended to do, because basically that is the last resort of failure or of safety before you lead into catastrophic mechanical failure, where you're having to have a lot of stuff remachined altogether because of that. You don't want to do that. So the proximity probe made it to where we can get an early detection before we're having to do a complete shutdown, and it gives us more higher reliability because we can be more predictive with what's going to happen. I hope that answered the question well enough. I hope that was to the point enough, and don't worry about the being too lengthy. Like we're doing good there. Kingsbury thrust. Yes, exactly, Henry. That is very very similar design. And the way the YK and the carrier compressors were, which would be what the 19 should be the 19XR style. Correct me if I'm wrong on that. Or 17M. Okay. Very very similar design and how they function. Very similar. And see, here's the thing. While there may be specific things that are, say, York in what they're doing, they're not as proprietary as we think they are. So a lot of these basic concepts are genuinely applicable across the board on a lot of different machines. They just have slightly different flavors on how they're going to go about doing the same basic idea. They're still probably using a bull and pinion gear design. They're still probably using a helical gear design. And they're still trying to step up, a single or a low speed motor to a high speed impeller if they're trying to do a single or even dual impeller design with a set of sleeve journal bearings. All of those basic concepts are still kind of the same, and Trane has their own versions of the same thing. Now, we commonly know the low speed version, which is the CV series, CVH F, the CVH and CVD series, right? Those are single shaft low speed machines, but they also have their own version of the high speeds, and they have their own version of the multi impeller, multi stage high speeds, and they're using helical bull gears to do all that. Like all of this stuff is just basic fundamental starting points, right? And then they can use that same technology and way of doing it in slightly different ways, and they call it like, this is our way of saying this is how we're going to do it. But in reality, a lot of the basic principles still apply. Like, it's still a bull and pinion gear. It's still a helical gear at that. And the reasons for that are still exactly the same reasons. Those aren't specific to York, right? Just like the thrust collar set up like that. That's not just specific to York and what they're doing. That is a way of designing this equipment from a base level. Now, I apologize for my sinuses. They've been giving me fits since the fire the other day, and I still have yet to get them straightened out. Oh, yeah, no, that'll wipe out an impeller in a heartbeat. That's the thing. These impellers, like, they're pure aluminum, but they're inside of steel housings. Aluminum gives to steel, if you didn't know. So one good touchdown, and if that thrust bearing, goes bad, or something happens with them and they don't prevent it, and you get one good hard touchdown, you, like, at 20 something thousand RPM at the horsepower we're running, that impeller is toast. Like, a couple of touchdowns, if not one hard one, and it's shredded. So yeah. Not good. 19 EA, okay. I feel like I read somewhere it's like -20 on the low end and 10 mils on the high. I think maybe. Yeah, that's sounds about right, Frylock. like I said, I don't want to say without actually going and verifying, because that is a very specific figure, and I don't want to accidentally give a misguided direction there by mistake. So what are the questions that we have? We're having a really good chat here, guys. I'm having fun. We've still got some more time. So yeah, what do you have? Hit me, hit me, hit me. While we're waiting on the next question, the service training program is live on chilleracademy.com. So if you've been interested in getting involved in that, you want to directly see exactly how I and an advisory team that I've got that's been helping me put this together, how we would go about approaching chiller repairs, troubleshooting, and service, how we would recommend doing different recovery styles, pressure testing, what are the parameters for these things. Go check it out. And if you get in there and you need a procedure, but you don't see a specific one, because, well, there's a whole bunch that we could make. That's kind of the point of the design. If you don't see the one you actually need or you're looking for, just reach out, let me know, and we'll get you fixed up with either writing it, ideally before you need it, or getting you the factory information you need so that you can go do it, and then we can work on creating our own version. Because that's one of the things that we're trying to do with it, more than just having a basic do XYZ the entire way through. We're actually trying to include a lot of the unspokens, and that's something I've really kind of taken to recently. The unspokens of our trade. There's a lot of little things that we learn along the way that we don't always, as we become experienced, we don't always think about to communicate, that somebody else hasn't already lived through. The rest of us in our own ways already have, so we can communicate a senior to a senior, and we understand because we've already lived through enough of those little smaller scenarios. But when we're communicating a senior to a junior tech, that's not always the case. And so one of the things we've tried to be very intentional about is, if there are some unspoken reasons why we go with X instead of Y, let's try to include that in there so that you have a better understanding of our intentions in the moment. Let's go also address tube failure causes. Yes, let's do that. Okay. Address tube failure causes. So, tube failures, what a tube failure means in the first place is that we've got whether it be in our evaporator or if we have a water-cooled condenser, either way. So being a chiller, you're going to have a hydronic evaporator. That is kind of the baseline definition of what makes a chiller to begin with. So if it's a chiller, it's a hydronic evaporator. So you've got a set of tubes in there on some level. And then you could have a hydronic heat or a condenser, water-cooled condenser, be another way of saying that. So there is a few ways to go about this, or as to why the tube has failed. You could have general erosion. So if you've got a system that is got a lot of debris in it and it's flowing a lot of heavy debris, whether that be mud, silt, whatever the case, other parts from the system, that can put a lot of extra wear on the tubing itself. And it's also going to mean you're having to brush those tubes far more often, which brushing the tubes as a act creates more wear. As more wear is added, you thin the wall of the tube. And eventually the tube wall can get so thin that it can't hold up to the refrigerant pressure and the water pressure anymore, and a leak is allowed to happen, or it ends up forming. So general erosion is one of the methods, and more than just, like, say, contaminants in the water system. also high GPM. So if you're flowing excessive GPM through your heat exchanger, then that extra water flow is going to add additional erosion because it's flowing through there far faster and harder than it technically needs to. And that puts more wear on your tube wall. Okay, so erosion of it is one way. Just straight debris causing a puncture is another. So Frylock knows about this one. There's a property that we've worked at that the pump strainers, some of them had collapsed and just disintegrated into a bunch of different pieces and made its way through the piping network. And most of the time, our pumps are going to be pushing directly into our chiller. So what happened in this case is those little fragments got into the condenser specifically, and they were big enough and sharp enough that as they went through the condenser, it just started punching holes on its way through, and that led to that technically it was two different chillers, but it led to having to plug a bunch of those tubes until eventually it just got to the point where we had exceeded the amount we could plug and still have any reasonable amount of function, in addition to just trying to stop the leaks in general. So having a debris that actually is able to puncture a tube is another way to have a tube failure. One of the saddest ways of having a tube failure is to have the tube freeze. Now, there's two cases where this could happen. One, you could have a genuine freeze at your facility. We actually had this happen in Texas, and it devastated us because we don't have the same winter protection, like winterization, that you have in other places, such as we don't run glycol in our loops. None of our loops are designed for glycol. We typically don't drain our loops, or at least we used to not, because the down period was so short and we had enough insulation that we rarely got cold enough long enough. And usually flowing water was more than adequate to protect our tubes in the winter time. When it got below freezing, we kicked the pumps on, flow water for that period of time, and we never had an issue. So what we had happen was the freeze happened. A lot of properties, their generators were not properly maintained. They failed, couldn't keep the pumps flowing, couldn't keep what heat trace we had flowing, and we had heat exchangers freeze up and bust everywhere. I mean, everywhere. It really wrecked us. So the tubes freezing. So basically, the ones that are most susceptible to this would be a flooded or a falling film design where the water is inside the tubes. And essentially when water freezes, it expands. Ice, it expands out. So if you've got your tube and we have a little bit of water that gets frozen in there and that water freezes, it expands and it just straight out ruptures that tube and busts it. So that is one way. Now, aside from just a freeze condition, if you're not careful or don't follow proper practices with recovery and charging, you will also create that same freezing condition, because essentially any tubes that are submerged below the liquid refrigerant, and that liquid refrigerant is allowed to get below freezing temperatures in saturation, which typically it's a common thing to have happen when you're recovering. Now there's ways of not. Again, if you're not following proper practices, you will very likely have liquid refrigerant making contact with tubes that still have water in them. And if you are not flowing water through those tubes, or if you have not drained that barrel, either way, that water that's sitting still will freeze and will rupture, and you've got a really bad day on your hands at that point. So call it malpractice, if you will, or just ignorance with recovering and charging procedures. You can freeze water in a tube and cause it to fail or rupture or bust. Another one would be, and I see Henry mentioned it there, saddle wear. So these tubes that are going through the heat exchangers, they're sitting in a set of racks, if you will. Let's call it that. And these racks over they can end up becoming a rubbing point. Depending on refrigerant conditions, depending on flow conditions, water flow. And I'll give a really clear example of this. The subcooler rack for a YK. It is very important that we maintain proper liquid level in the condenser for a YK, because the if the refrigerant level drops too low, it creates a lot of currents, or specifically eddy currents, inside of the subcooler housing. Those eddy currents will allow extra turbulence to rub on the tubes, and that extra rubbing will eventually lead to a hole being rubbed in a tube because of the rack, and then that leads, obviously, to a hole in tube. You had a failure, right? And then your water and refrigerant start to mix. So that's an example of a situation that can happen, that where if not managed correctly, the tube can rub and get a hole rubbed in it from the rack assembly itself. Now, another one is the actual end plate itself. So due to expansion and contraction from the water cycle of heating up and the chiller shutting off, shutting down, different seasonal shifts. So anytime that metal is getting hot and cold, so you've got a steel end plates for the tube sheets, and then you've got copper tubes most of the time in what we're working on. Well, those metals expand and contract at different levels or at different rates. So enough of that over time, or just general vibration and where high excessive flow can cause additional vibration that can contribute to those tube sheets where the tubes themselves are swedged into the end plate. Those can become leak points as well. More than just the internals of the tube between the two end plates, the actual end plates themselves, where the tube is swedged to the end plate, can also become the leak point. So these are a variety of set of ways that a tube can fail, or tubes, depending on the circumstances. And depending on the type of failure, depends on what we can do. So the most common thing to do is, ideally, you catch it early enough where it's not a catastrophic failure, ideally. In that event, you're going to plug that tube with a set of plugs. Now, to do that, you're opening up both sides of the tube sheet. Okay, so that'll just kind of depend on your piping, on how difficult that will be, whether it's a 2-pass or a single pass or otherwise. But you're going to open up the both ends of the tube sheet, and then that particular tube that is leaking, or let's say you had an eddy current test done and you found that you had a couple of tubes in there with a really thin wall, so they were dangerously thin. Then we're going to put a little bit of sealer on a plug. So the 515 by Loctite would be a popular choice for this. Put a little 515 on it, and you're going to hammer that plug into that tube and ideally stop it. Now, before you put the plug in, it is recommended to use some nitrogen or something and try to blow that water out of there and dehydrate that tube ahead of time, so that if a failure did end up happening, whatever moisture is in there isn't able to get into the machine, and vice versa. So yeah, plug your tube sheets. That's one of the most common ways about it. Now, if you had a catastrophic failure, which I've seen some of these where it literally floods the chiller. So first of all, the refrigerant, now if it's a high pressure machine, the refrigerant's going to flow out into the water circuit. But a low pressure machine, water's just coming straight in. And so um, in a catastrophic event, that I've literally seen, I've had pictures sent to me of CVHs that the water level was up into the suction nose cone. Just at how much had filled up in the chiller and then set there on top of that. So that would be catastrophic. Like that'd be the definition of catastrophic. In that event, you've got to do a complete overhaul of that entire machine. So if it was that bad, more than likely it's going to be worth it to have the machine retubed at that point. And there are companies out there that specialize in this. I personally have not done a retubing myself. But at the same time, unless you have a team internally to your organization that does that, there are some really good companies out there who do that very, very well. So, in the process of trying to rebuild this machine and put it back together, it's going to be recommended to do a retube. And if you're going to do a retube, you're going to redo all the tubes. Like that is my recommendation. Like you're not just going to do the ones you think that are bad, because the cost of going to that extent to begin with to bring that machine back to life is not worth the risk of leaving old tubes in place to begin with. You end up going through and just doing all the tubes new so that everything is fresh, and that's a very extensive process. But yeah, those are, if you had a failure, either plugging the tube or, depending on the extent of the failure, potentially retubing the machine are going to be the primary ways of getting that leak to stop or not having it affect the rest of the machine. And if you had a tube sheet leak where it was leaking at where it's swedged into the end plate, then a lot of the time I've found that doing the plug and putting the plug in the first place is actually enough that it will inevitably seal. Not always, but I found that that is a common way to get one to reseal without having to literally re-swedge it, is just putting a plug in the first place forces that swedge to expand out and reseat into the tube sheet itself. Excellent question. Excuse me. Complete hands, complete tear down. Yeah, it's a very, very big job. Oh, there's some machines. It makes me cringe. I've seen the pictures, and just shiver right down the spine. It's just like, wow, that happened. I can imagine. I wonder what the cost difference is between replacement and rebuild and overhaul. This is a fantastic question. This is a question that comes with much debate, I would say, uh, depending on uh, depending on the who you talk to. Okay, what I wonder what the cost difference is between replacement and rebuild slash overhaul. So this is really um, this is really circumstantial, like heavily. A lot goes into making this decision. I mean, a lot. So the scale of the machine would be one thing. Some of these chillers are, they start off in the, now I guess if any kind of scale and size, they're hundreds of thousands typically at the smaller scales, and then they scale into the millions depending on the size of your equipment. Now, and that's also true for the overhaul cost. Your smaller machines are easier to overhaul, and they're going to cost less. The parts are also a little bit less compared to If you had a larger tonnage, say a 2,000-3,000 ton versus a 1,000 ton, right? There's a quite a bit of difference in the amount of people required, the size and the weight of what's being lifted, and the safety standards that are going to have to be into place, and the rigging needed to do the lifts. Like, there's a lot of details that goes into that. So the cost will vary heavily. A 500 ton to 1,000 ton machine, doing it, at least in my region, it costing 80 to 120 grand, depending on the specific machine, is pretty typical. That's not an unreasonable overhaul cost for that size of machine, and that only scales. So then you have to take into account, okay, this is how much it's going to cost in the timeline. Okay, so timeline has an effect here of an overhaul versus getting a new machine spec'd, getting it ordered, getting it built, getting it shipped, then getting it installed, and then commissioned. Yeah, you get warranty and stuff and with it, but you get warranty typically with an overhaul style of repair to begin with, right? Granted, it may not be a factory warranty, but the contractor that did the work is still going to be responsible for the work done on some level. So even the warranty thing, you could kind of take here or there. It has been my experience that, especially the larger the machine gets, the more true it becomes. The time and cost required to get the new chiller, because especially in the context of this chiller is already down, it's already dead in the water, and we really need it now. The turnaround time and cost for a new chiller is significantly higher than what it would be for the overhaul. And with the overhaul, we can get this machine back online faster and cheaper. But the faster, in a lot of circumstances, ends up becoming the big thing. When you have a conversation of, okay, it's gonna take us a month to get everything to do this overhaul, and have, you know, within the next month and a half, we can have you back online in an extreme case. That versus, hey, it's going to be 6 to 8 months, if not a year plus, before the machine's even going to be built at the factory, much less shipped to you, and we get to install it. That timeline alone is enough to make most critical facilities say, okay, well, buy a new, that's just not going to work. We can't be down for that amount of time. We've got a data center. We've got whatever process we've got going on here. We've got to get this back online. Month and a half, far better outcome. Is that painting a picture? Also keep in mind that depending on the needs of the overhaul, you can get a... Okay, how about this? Let me take a step back. Centrifugals, as an example, are built to hold up and last significantly longer, and are built far more robust, in my opinion, than what we would expect to get out of other equipment. So would it make sense to completely strip down and rebuild an RTU, a split system at somebody's house, or even most of your air-cooled chillers? The answer is no. The conditions those chillers operate in at the same time also put a lot more stress on them, because they're out in the elements most of the time. Whereas these centrifugals that are water-cooled, they're out of the elements usually, so they have less wear on them from that perspective. And they're made to, like, these are 30, 40 year machines. They're made to be taken apart and completely put back together, and they'll function just like a new machine almost, if done correctly. If done correctly. And you can do upgrades to these machines, right? You can take an old machine that was a single speed um, starter package, and you can upgrade it to a variable speed. You can upgrade the control systems, and the manufacturers sell these components to be upgradable. So that's one of the selling points and the benefits to going centrifugal in the first place. These machines, when used and repaired correctly, I think is kind of the major point here, they can be a career-long machine in ways that you wouldn't expect these others to do. Like your condenser coils are going to be the main thing on air-cooled systems, whether that be air-cooled chillers, RTUs, splits, whatever. Those are going to, the cost to fix those is going to be so astronomical. That alone is going to remove a lot of the cost benefits to fixing something like that, where you don't have that with these water-cooled centrifugals. So most of the time, once everything is hashed out, the overhaul ends up being the better choice. It just does. And usually when you see a water-cooled centrifugal getting replaced, it's usually because it's at that 30, 40-year mark, and they just may not even make the parts anymore. They just flat don't make them. And they hadn't for 5 or 10 years. So the backstock inventory might not be there anymore. Or it's an efficiency thing. Like, so there's been some I've seen that were, say, in their 20s time frame, but when they were made, the efficiency was significantly less compared to what a modern machine could do, especially if they wanted to go mag bearing. So at that point, as long as they can wait for the manufacturing process, the efficiency gains, which in today's market has there's a lot of rebates and stuff with improving efficiency of the building. They don't really care about the repair cost. That's not their problem, as long as electrically it's more efficient as a system, right? That's really what they're hyper focusing on. So that can be another area that tips that balance between this is worth it versus this is not. But again, the mag bearing side of things, short of the YZ and some of the newer equipment, that's going to be your smaller machines at that, because mag bearings, other than the YZ, haven't really scaled to those larger sizes yet. So the cost benefit and overhaul on those smaller machines is already kind of tilted. Yeah. Hopefully that makes sense. Hopefully that explanation was clear enough. How about that? It is something that causes a lot of debate, because there's a lot of thoughts from a lot of different camps on what should be the go-to. But in my experience, it comes down to turnaround time compared to cost. And usually I've seen turnaround time be the primary factor that ends up winning. If it's a fraction of the turnaround time, they will go with that instead. Anyway. Okay. Is there a final question? We need to get to wrapping this one up. So is there a final question we can hit and then call it good? Anybody got anything? Anybody have anything? What factors usually trigger an overhaul? So you keep asking these long questions, man. They're good questions, but they're so long. I'm just kidding. I'm kidding. I'm kidding. All right. Okay, so what factors usually trigger an overhaul? It's going to come down to your bearings. Um, your bearings are going to be the number one thing in most scenarios that result in an overhaul. Now, this is if there is a failure, okay? Assuming there is a failure. Your bearings are typically the first thing to fail, whether it be your thrust bearings, whether it be your sleeves or your journals. You're going to see that in your oil analysis, and even your oil filter. You're going to start having a lot of flaking. That machine is going to have a lot of extra vibration and just operational noise that wasn't there previously. All of those things are going to point to we're starting to have a bearing issue, and we want to resolve this before we have an impeller issue. That's a whole nother level of issues. So there are other things though. So if we're having trouble getting lift and moving the refrigerant, and the machine is even having trouble to function, we could be having an impeller issue. There could be something like we may have had a touchdown and we messed up some of our vanes, or we could have slugged back or had droplets come back and start shredding the internal of the impeller, right? So we ran our liquid levels too high, or something happened on the load side that allowed us to mess up the impeller on the by allowing liquid refrigerant to come back in. We could have an eye seal issue, a labyrinth seal, where we're bypassing the high side directly into the low side. All of those conditions where the compressor, while technically should be loading up, say we're on a variable speed, but we're at our 60 hertz, or all of those factors are true. IGVs are open, impellers open, all these are true, but yet we still just somehow the compressor ain't compressing. Those would be conditions that would make you say, okay, well, something has happened. Or in the event of the impellers getting tore up, you'll have issue maintaining lift. That you'll get into these really low lift conditions where under normal circumstances you'd run just fine, but the compressor just can't do it. It can't. As soon as it begins to build lift at all, it starts to having surge issues, right? In the most extreme cases, that a tore up impeller, whether it be from touchdown, whether it be from liquid, that's going to be more symptoms of that. So all of those would trigger a overhaul from a failure perspective. Now, there's a lot of facilities that do this on a routine. So 60 to 80,000 hours is the industry standard for when you should do an overhaul. To be honest, there's a lot of chillers that, if they're treated correctly and they're in a proper environment, they're commissioned well, they will run for 100,000 plus hours and never need an overhaul. They're fine. So in most of the cases that I see that 60 to 80,000 hour recommendation is stuck to the most is in critical plants. Okay, so we're talking data center environments. We're talking critical manufacturing processes for large facilities, stuff like that. I'll give an example. The Samsung semiconductor plant in Austin, Texas. They've got, I think it's 20 or 20 something CVHs in there. And they're all, I think, 2,000 tons each. And they run them in different seasons. And those chillers are on a routine cycle. That's a semiconductor plant, and their necessity to control a very pinpointed leaving water output is extremely, like the scales. Like, if you haven't been in those environments, the scales at which we have to flow or keep a precise control of our leaving water conditions gets wild. Okay, but it depends on the manufacturing process itself and how how much tolerance there is before you start messing up their product, because you get too far outside of those ranges. Now their product is being affected, which is hurting their bottom line in the end. So having chillers down is not an option. So in that environment, they go through a routine overhaul cycle, whether the chiller has symptom signs or anything or not. They go in on a schedule and they just do a continuous overhaul cycle of those centrifugals to prevent downtime as much as possible. So that's usually where I see the time frame used the most, is in those critical facilities circumstances where they can't afford that. The cost of downtime is way more than a simple overhaul that we already know is probably going to be fine, but we're going to do it anyway to make sure. So yeah, those are the two directions you will see. You'll have to go into on when should an overhaul be performed, and that depends on the facility and site that you're at. Okay, awesome stream, guys. Really enjoyed hanging out with everybody. It's feel good to get back into it. Back into the swing of things. I'm very excited about the service program getting launched. We've put a crazy amount of work into putting that together and getting it where it's at now. And this is only the beginning point. This is something where it's going to continue to grow and build as it goes. And as you need procedures and things, that was the whole point and intention from the get-go. Let's get a baseline in there that gives you something to start with. And then we will create procedures and give you guidance and do what you need so that you are successful and you don't have to worry about failing at it. I guess the biggest thing I want to avoid for you is I don't want you to fail. And this is one way that I can provide a resource to make sure that failure is not on the table for you. That's my goal. So I know it's what I needed. Absolutely. Either way, really appreciate everybody. In MTT, make the time for your family, for your spouse, and your kids. We're going into busy season. This is a very demanding, very difficult industry, and it's going to require a lot of us, and we have to just make the time for them and for what matters to us. The time's not just going to be there. It's never just going to be convenient, and sometimes our boss isn't going to understand, or he's of a different mindset. It is what it is. It is our own responsibility to make the time for our family. And we have to do that. So please take the time for that this season and this year. Be careful out there.